So this video is an introduction to thermodynamics, and we're going to look at endothermic, exothermic reactions, calculate how much energy is given out when a fuel is burnt, define enthalpy change in standard conditions, and define enthalpy of combustion and formation. And then in the next video we'll go into more details on things like Hess's law. So exothermic reactions are reactions that release energy into the environment, such as combustion or acid-base reactions, or even rusting. Although it's really slow, it's also exothermic. Endothermic reactions are chemical reactions that remove energy from the environment. So they are things like photosynthesis. It takes in energy. This is an example that's showing ammonium chloride and barium hydroxide. It gets down to the minus 24 degrees. It's really quite an impressive demo. So whenever a chemical reaction takes place, bonds are broken and bonds are formed. So it's a common misconception. People think, oh, exothermic, that's when bonds are formed, endothermic. No, in both of them you have bonds being broken, both of them bonds being formed. So when bonds are broken, you have to supply energy. So energy is taken in when bonds are broken. Energy is released when new bonds are made. So when this green one comes together and forms a bond with this blue atom, energy is released. So a reaction that is exothermic is where more energy is released than is supplied. So in an exothermic reaction, energy is required to break bonds, always, but more energy is released than is taken in. For an endothermic reaction, more energy is taken in to break the bonds than is given out when new bonds are formed. In an endothermic reaction, we still have new bonds being formed. There is energy being released. It's just that more energy was required than is taken in. So overall, it requires energy. So this diagram shows either an exo or an endothermic reaction. Well, you can pause the video and have a think. Basically, you've got energy going up the side, so you can see that the reactants have lots of energy and the products have less energy. So therefore, energy must have been given out. So you can see first energy is required, first energy is taken in. So this is for breaking the bonds here. So energy is taken in to break the bonds, and then loads of energy is given out. So overall, this is an exothermic reaction. So this one, we can see we've got the reactants with a little bit of energy, the products have got more energy. So you can see loads of energy is taken in to break the bonds, and some energy is given out when new bonds are formed, but overall, more energy is taken in. So this is an endothermic reaction. So thermodynamics is the study of heat changes during a reaction. And the quantities matter. So the amount of heat given out depends on the quantities of the reactant and is measured in kilojoules per mole. So have a look at this reaction. You've got some methane reacting with some oxygen. So that's combustion, forming carbon dioxide and water. Okay, so this reaction gives out 890 kilojoules per mole. So every mole of methane that you burn, you get that. Okay? So if you burn 2 moles, you get double that. Or half a mole, you get half that. So how much heat would be given out if 100 grams of methane was burnt? That's going to be a subscript there. Well, you need to work out the moles. So how many moles do we have in 100 grams? Well, you should know, you want to work out moles. So moles equals mass divided by mR. So we've got moles equals mass divided by mR. So mass is 100. mR is going to be 16, carbon is 12 plus 4 hydrogens, so 100 divided by 16. So you've got 6.25 moles. Okay, so how much energy is given out? Well, you just times that by the 890. So energy given out, moles, times the energy given out per mole. So it turns out that if you burn 6.25 moles, you give out 5,562 kilojoules. Oops, there's a mistake here. It shouldn't be per mole, it's just kilojoules. So this is the amount of energy given out. So have a go at the following questions. Video. Answers to follow in a sec. Here are the answers to those questions. Here are some more questions to try. And again, the answers to those questions. Okay, new word. Enthalpy. So enthalpy is the energy transferred when a chemical change happens. It's measured in kilojoules per mole, kg per mole. That should be a superscript there. It's measured as a transfer of heat under constant pressure. Okay, so the way we show enthalpy is with this symbol delta, that's capital delta H, that's for enthalpy. This little symbol here is theta, and it's to signify that it's happening under standard conditions. So you put a value in here, so for example it might be 890, and that's kilojoules per mole, and that is the enthalpy change. And you generally give this a positive or a negative sign. So a negative sign would be if it's exothermic, and a positive sign would be if it's endothermic. So for the previous one, it was exothermic reaction, so it would be negative minus 890. Okay, some definitions, and what does standard mean? So standard refers to standard temperature and pressure. Standard pressure is 100 kilopascals, that's what you're feeling right now in a normal room, at normal sea level. And standard temperature is 298 Kelvin, or that's 25 Celsius. So definitions. Standard enthalpy of combustion, it's written like this: delta H, theta, for standard conditions, and then C, so it's for combustion. Okay, so the definition for the standard enthalpy of combustion is as follows. So it's the enthalpy change when 1 mole of a substance is burnt completely in oxygen under standard conditions, all substances in their standard states. This is a very, very common definition that you'll be asked, so you need to learn this word for word. Best thing is to make some flashcards. There's a few other ones you need to learn. The next one is enthalpy of formation. So enthalpy of formation is delta H theta, standard conditions, F formation. So it starts off the same. It's the enthalpy change when 1 mole of a substance is formed from its elements under standard conditions, all reactants and products in their standard states. Or all substances in their standard states will equally be as good as. In A2 you'll learn a few more, but these are the sort of main 2 that you need for AS. And standard state means whether the substance is normally a solid and liquid or gas at room temperature. So in formation data, when you're forming the elements in their standard states, you must form it. So for example, if you're forming it from water, water's standard state is a liquid. Carbon's standard state is solid, and it's graphite. It's a standard state. Hydrogen might be as a gas, it's standard state.